Now we're going to talk a little bit about continuity. And so there are a series of questions that I want you to answer. So kind of pause the video, and the video is going to have some questions, and please answer them. So the first question is, what does it mean for a function to be continuous? What does it mean for a function to be continuous? So think about it and answer this question. What does it mean for a function to be continuous? So you might think back in pre-calc and say if the function doesn't have a break, or you can draw this function, so you can draw this function without lifting up your pencil. You can also say something like there's no hole, something like that. So all of those means that the function is continuous. Okay, sketch 2 ways for a function to not be continuous at x equals 4. Can you give me 2 ways where this function is not continuous at 4? Okay, so maybe one way you did is at 4, you said there is a hole. So it's not continuous. That's great. Maybe another way you did is that you put a asymptote at 4. That is also great. That is not continuous. What else can you do? Those might be the main 2 ways, or actually you might even think that you can do a jump discontinuity. So like that is not continuous. So 3 ways, or if you found another way, that's also fine. Next question. Keep the graph there. Write one way you can make your graph continuous. What's one way you can make this graph continuous? Well, let's look at this graph. So remember, to be continuous means that there is no break, right? If you draw this graph with your pencil, you don't have to lift up your pencil. So if we look at this one here, is there a way to make this graph continuous? Yep, if I just fill in that hole, it will be continuous, right? Great. Let's look at this middle one. Is there a way to make this continuous? No. There's nothing I can do to connect the 2 graphs together. No matter what I do, I will still have to create 2 graphs. I cannot like combine like that, because this actually goes up and down forever. So there's nothing I can do to connect the 2 sides of that graph, so there is no way to make it continuous. What about the third one, the one on the right? Is there a way I can connect the 2 graphs? This one is also no, because even if I fill this hole in, it's still not connected, and there's no way I can bring this gap together, right? So then that means this one is not possible to make continuous. So the only one that I can actually change to make continuous is the left one. All right, now let's go ahead and try this next one. Erase the graphs. Draw a function with a removable discontinuity at 4, 3. Removable. All right, at this time, I think a lot of people forget all the continuity names. Okay, so continuous. Continuous means you draw the graph without taking your pencil off. If it doesn't have that kind of form, then that means it's discontinuous. And to be discontinuous, there are a few types. First, we have a removable discontinuity. Removable discontinuity means that there is a hole, like that. The second one is called the jump discontinuity. Okay, so I know at this time maybe some of you are thinking, hey, there was another removable discontinuity in pre-calc. You're correct. There was one where I said there was a number that's defined somewhere else, which is also true. That is also called removable because it has a hole that exists between 2 lines that should have been connected. Okay, So jump discontinuity means that your two graph actually splits, and one of them has a hole and the other one has a point, or it doesn't even have to have a hole, but just like it's disconnected so to the point where it splits with a jump. And then the last one is the infinite infinite oh sorry infinite discontinuity. Infinite discontinuity means that we have something like a asymptote. So this one we can never bring together. So we're going to, I'm asking you to draw a removable discontinuity at 4, 3, a graph that looks like that. So pause the video and give this a try. So removable discontinuity at 4, 3 means something like this. Removable discontinuity, not a jump, not a infinite discontinuity, removable. Describe the discontinuity with a limit statement. Let's try this. So this is the limit as x goes to 4 from the negative side of this function is equal to the limit as 4 goes to x goes to 4 from the positive side of this function, and that is also to the limit as x goes to 4, and they all equal 3. So kind of like what we learned prior to this. If you do want to make this graph continuous, what do you have to do? If you want to make this graph continuous, what would you have to do? Very simply, fill in that hole, right? So, the last part. Now write a definition using limit statement describing a function f of x that is continuous at x equals a. So kind of the question is, what is the difference between this graph that this graph that had a hole versus this graph that had the hole filled? What is the difference? Well, it's very clear that one the difference is that one has a filled hole, one doesn't have a filled hole, which means this one is continuous and this one is discontinuous. And so both of them would have the same limit statement, correct? Because both sides of the function going to 4 are the function from both sides are going to 3. So coming to 4 from both sides, the y values for both graphs, right, continuous or not, they're both going to 3. So then how would you be able to distinguish one that has a hole and one that does not have a hole? And this is kind of the main idea of discontinuity. The main difference is, so the similarity is that the limit is the same. The difference is for this one with a hole, the limit does not equal to f of 4. For this one, the limit is equal to f of 4. Remember, f of 4 means what the actual value is at 4. For this function, not defined. For this function, there is a number. So the main difference is on the left, there is a limit, but at that limit, there is no number. On the right, there is a limit. At that limit, there is a number, and the numbers are the same. If they're not the same, then it becomes this situation. There is a number that exists, but it's not the same as the limit. All right, so here is the main idea. Continuity condition says a function f is continuous at c when these three conditions are met. First, f of c is defined. We have to have a number at c. Second, the limit at c exists. And how do you prove that it exists? The left-hand side of c is going to the right-hand side of c, and therefore that is equal to the limit at c. Okay, that's the second thing. The third thing you have to prove is that the limit at c equals f of c. Okay, now let's kind of review continuity a little bit and think about it. So let's say that if this is true, the limit as x goes to a of this function is equal to f of a. What does that mean at x equals a? Does that mean the function is continuous everywhere? So there are two questions. First, what does it mean at x equals a if this is true? And the second thing is, does that mean the function is continuous everywhere? So go ahead and answer those questions. All right, so let's answer the first question of part 1. So what does that mean at x equals a? So we talked about that if limit at this function at x equals a is equal to f of a, meaning the limit exists, which means both sides are going to the same number, and at x equals a, that number is exactly the same as the limit, then we can say that it's continuous. Is that true? No. Continuous at x equals a, because all we did was we only proved that at a, the limit and the number are the same. Okay, so then that kind of leads to the second thing. Does that mean the function is continuous everywhere? We don't know. We know that it's continuous at a because that's the only information that's given. It could be discontinuous elsewhere. We don't know, right? Because, like, for example, let's say they gave us this information here. The limit from both sides is equal to the actual point, so we know at that point it's continuous. Is it continuous everywhere? No. There is another place where there's a hole, so we cannot conclude just by a limit statement that this whole function is continuous. Okay, so please be careful of that. Number 2, if a function is continuous, does it mean this? So the question backwards, right? The first question is, if I give you this limit statement, does that mean at x equals a it's continuous, or is the function continuous? Now ask backwards. If the function is continuous, does that mean this? So think about it. Okay, if the function is continuous, does that mean the limit as x goes to a of the function is equal to f of a? Yes, of course. That is the definition of continuity. If the function is continuous everywhere, then at every single point, the limit must equal the actual value.